Good morning again, everybody, and welcome. Today is May 18th. We have chapter 26. I know I posted the stuff related to chapters 20 and 21. And sorry for the mix-up that we did them a little later, but you guys have them on Canvas. We still have 3 chapters, really. All of them has to do with astronomy. The first one is just on the solar system. The next 2 chapters are, let me look them up to make sure I give you the correct information. They are on stars and galaxies. Basically, the first one is on the solar system by itself, which is a big topic. The second one is the stars and the rest of the universe, which is a big topic by itself too. And the last one is the structure of a space-time. So basically, all of them have to do with astronomy. As I said, the first one is on the solar system, which we're going to be doing today. And the next one is on basically the physical structure of the universe itself, the galaxy, the other stars in the galaxy, and what we know about them. The last one is about cosmology, basically the evolution of the entire universe and also the space-time structure and what we know about this thing. So it's a big topic. Always, amazing for me, to think about where we were on February 16th when we met first time around. We barely started talking about physical concepts and causes of motion and basically in 1D and what causes it to change, and we introduced Newton's laws, all the way to at some point we're discussing the entire universe. This is amazing. I always kind of fascinated by this thing. Within like 2-3 months together, we go through the entire everything. We do chemistry, we do geology, we do structure of the atom, the nucleus. We go into basically the things that we're going to introduce today to the solar system, big stuff, the entire planet Earth, which is everything we know and we have known and we probably will know forever in terms of our immediate connections. Everybody you know or read about or anything that happened is on this tiny rock. Okay, combine that with the other rocks in the universe, in the solar system. You have basically at least, forget about the sun, which is a huge powerhouse where all of the energy that powers the entire solar system is coming from, for the most part. Then you have this big rocks next to it. You have 4 of them of a rocky type, namely Mercury, which is a big planet by itself. Don't be fooled by the fact that it's smaller compared to the other 3, I'm sorry. But it's still a big planet. Then you have Venus, which is really almost the same size as the Earth, slightly less. It has a completely different, basically, look to it, in a sense that it has a super massive atmosphere dominated by carbon dioxide, which is highly toxic for any life that we know. And its surface temperature is so high because of this extreme high pressure. It's about 90 times that of the pressure of the Earth in there. So it would be crushed if you were going to stand on its surface just by the pressure alone, let alone the temperature. And then comes the Earth. It seems to have all the right conditions in terms of life basically evolving on it. And although it shares the same neighborhood with Venus in terms of suitability for life, but for some reason, Venus has basically no chance whatsoever to see life of the same form that we know it, okay? And I emphasize that word because maybe there are other forms that we don't know about. So the maybes start to become more and more because we don't really have firsthand, other than the fact that we sent probes. They didn't last too long on the surface of Venus because of the fact of the extreme conditions that it is on it. And so we're hoping more and more studies. Obviously, we were able to send radars and map the surface and things like that. And we have an idea of the elevation on the planet, the temperature and all the structure in terms of also being extremely acidic. It's not just carbon dioxide that is toxic in there. There is also acids, extremely bad conditions on that planet. Then you have Mars. Mars, in terms of studying, is a lot easier, although it's further than Venus. Venus is actually closer, but it's further. But it's in terms of we can land an object on its surface, and it can survive that surface for a long time. Case in point, we have a lot of Mars landers, orbiters. We have sent all kinds of things to it. So those are four fascinating objects. Both Mars and the Earth and Venus are in the habitable zone of the Earth, of the Sun. So in a sense that they all could potentially have life on them. But for some reason, Mars is smaller, and it lost a lot of its conditions for life suitability. So it's not really, it's hostile to life, extremely hostile, okay? Because of extreme temperatures and lack, for the most part, of an atmosphere. I mean, it has an atmosphere, but it's very tiny compared to the Earth. Mars is actually is exposed to cosmic radiation and solar radiation, which are extremely dangerous for any life that we know of. So it seems like the Earth is really the lucky thing. In terms of density, it turns out the Earth is actually the densest planet in the solar system, period. Denser than the Sun, at least for compared to the outer, I mean, on average, denser than any other planet, including Jupiter, by the way. Okay, including all of the other big giants. The next one in terms of density is, as a matter of fact, is Mercury. So it's kind of an odd thing in here in terms of the solar system. Then comes the outer planets. The outer planets are super big, huge planets, I mean, in terms of size. Jupiter is by far the biggest one. Jupiter is a huge planet by any sense of imagination, much, much bigger than all of the other planets combined. That including Saturn. Saturn being a huge planet by itself too. However, Saturn has unique features in terms of, for example, its density. It's lighter than fluid, than water. In a sense, if there is an ocean big enough to hold it, and there is nothing that we know of that size, it's actually going to float because of that, it doesn't sink. So we have all kinds of fascinating planets. All of the outer planets, Jupiter, Saturn, Uranus, and Neptune, they have rings around them. The only one that is obvious to our eyes is the one for Saturn, but all of the others do have rings. They have extremely high winds on their surfaces. They spin fast, faster than the Earth. The only planet that spins almost the same speed as the Earth is actually Mars. The day on Mars is almost slightly more than 24 hours, slightly longer than our day. But everybody else, I mean, like if you take, for example, other planets, for example, Mercury and Venus, their day is actually longer than their year. So it's kind of weird structures in that. All of the other planets, they spin in the orbit around the sun, the same orbit called the ecliptic. If you look at this, then they will go around in almost the same circle. And they spin going around the sun in that direction, plus they spin around their axis. Some of them are tilted more than the others. That tilt determines the seasons. The Earth has 23.5 degrees tilt, which makes it ripe for changing seasons. We have 4 distinct seasons in the year. Whereas, for example, other planets are actually backward. Like, for example, if you take Uranus, it's almost at 90 degrees opposite to where it's supposed to be, okay? So it's spinning, it's going on this ecliptic, but it's spinning this way while it's going. So it's really a different structure, which suggests that there are, if we look at the history of the solar system, that maybe there is something that happened in the back, because if we take, for example, the conservation of angular momentum, concept that we saw a long time ago when we first started, probably in March, okay? Now, we're using that concept to understand that why all of the planets are actually orbiting the sun in the same direction on the same plane. And that is because of the conservation of the solar system. In a sense, the solar system was a big, giant, probably gas, and because of the collisions, they collide and they form more and more massive objects, the first one being the sun in the center, and then the other planets start to form. The first one probably is Jupiter because it accumulated a lot of mass, and then the other planets start to form after that, and to a point where the sun gathered a lot of material basically around it, namely mainly hydrogen and helium, for the most part hydrogen, that is the main thing, because of the density that started to increase extremely high in its center. High density, extreme high temperatures, there were ripe conditions for nuclear reactions to start in its core. In doing so, it exploded and basically kicked most of the gas out of the solar system. So whatever you gained at that point is your size. Since the big giants started earlier in the process, they gained more material than the other tinier planets, and that's how Jupiter basically. If the sun did not go nuclear at that point and waited a little longer, most likely Jupiter would have gathered more hydrogen and helium in it, and probably it could have gone nuclear, and we would have 2 stars in our solar system. So instead, we ended up with 1, basically. So that is basically the story in a nutshell of the solar system. So that is really, now you ask, what happened to the Uranus? Why is it flipped backward? Well, in this case, most likely it went in a big collision with another object, most likely a moon or another small planet that was forming at that time, and basically flipped it on its side. So that is basically what we understand in terms of the solar system. And that's not the whole picture. We have tinier objects. We have dwarf planets like Pluto or Eris or other smaller objects in the Makemake and other objects in there. So those are smaller, basically dwarf planets. So the fact that they are dwarf does not really minimize their effect. I mean, they have moons. They have a lot of moons, some of them actually more than the inner planets really don't have any moons. The Earth is an exception to the rule. Venus does not have any moons that we know of. Mercury does not have any moons. And then Mars has a couple of moons, but they're actually captured asteroids. One of them is going to ultimately fall on Mars, and the other one is going to escape its port completely and basically be free from it. So, but the other ones have a lot of moons, which is another topic by itself, because the moons are a lot of them. Jupiter itself has 70-something moons that we know of. The biggest, of course, are the 4, Ganymede, Callisto, and Europa and Io, where Galileo discovered them with a toy at that time that kids used to play with, the telescope. So that is basically the solar system in a nutshell. The solar system also is surrounded by 3 big regions of rocks, mainly, or other debris. The first one is the asteroid belt, and that exists between mainly Mars and Jupiter. And then there is the Kuiper belt, where most of those dwarf planets exist, and it's very, very far from the sun. They take a long time to spin. And after that, there is even a cloud, and all of this first. Whether I'm talking about the asteroid belt, whether I'm talking about the planets, whether I'm talking about the Kuiper belt, for the most part, they exist on the ecliptic, the same plane. And because of the fact that the gravity and momentum was really at play there, that's why they do that. But when you go further away from the Earth, from the sun, there is a big cloud that is completely basically like a 3-dimensional sphere that extends very far actually to interstellar space. And that one is actually where it has all kinds of weird geometry. Like a spherical shape, more or less. It's not like uniform like the others. And because those objects are very far away, and that's probably actually not there. I'm sorry. In Kuiper belt is probably where there is that hypothetical planet 9 is probably lurking in there, very far away from the sun. So that is basically the story of the solar system. There is a software I'm going to share with you. I'm going to put it on the share in here. I would recommend that you install it on your computer. Okay, it's called Stellarium. It's for free. If you put it on your phone, first of all, it doesn't work as well as on your computer, and you have to pay for the version on the phone. It's like $2, $3, or $4. I don't remember how much I paid for it. But the one on the computer, whether you have a Mac or Windows, this software is 100% free. I'm going to share with you the software because it gives you in real time how your location looks like. So if you own a telescope, And there are telescopes out there that are not expensive at all. Like, for example, from Astronomers Without Borders, they give you a nice telescope, a 5-inch telescope, collapsible actually, telescope, Newtonian telescope for like $200, $199. So you could collapse it, put it on the trunk of your car, does not take space at all, and go wherever you want to, open your laptop, since you are in that location, start looking for objects and start looking at them. It's a really fascinating software. I love it. Okay. So in the old days, I don't know if we were meeting on campus. I don't know honestly about the Norco. I think Norco doesn't have a lot of equipment, but I taught the astronomy class in Riverside, and we have there a nice planetarium where you can actually see the skies during different dates and so on and so forth, and you can track objects. So let me share with you the software. Let me first of all pull it. Stellarium. It's loading. Okay, so let me share Stellarium. So this is how the software would look like, basically. As you can clearly see from the bottom in here, it says Earth, Loma Linda, 0 meters, because it actually knows where I am, and it knows that I am in Loma Linda. So if I want to, I could change the location to a different place. And based on that, you have to use your mouse in here and find the where you are. Okay, so you can go to a location, and based on that, right now it points to exactly where I am in here. You can look for, I don't know, Norco. So it found it. Okay, so if you are in Norco, if you are in Riverside, you can find your location. If you are going to go tomorrow to, for example, I don't know, New York, for example. So if you're going to happen to be going to New York, you just put the name of the location, and it's picking up a lot of New York stuff here. Okay, like we're going to be picking up the state actually. So you can pick up whatever location you're going to be in and find it in there. I don't want to change the location, because if I do it, then I'll have to find where I am at. It gives you the geolocations for where you are. You can even enter your height in here based on the ground. I don't know how many are in here. 600 feet is about what, 200 meters? Let's put it to 150 meters. Can I do it manually? Yeah, I can do it manually. Okay, so this is probably roughly where we are right now in terms of location. And that's it. So right now, this is the location where we are. So make sure you connect it to your own location. Right now, also the time on the software, it's picking up the current time right now, and it's actually on this date. It's using the military representation of the date, which is fine. You can change the clock to simulate what happened, for example, tomorrow, okay, on the evening. And any time that you would want to, you can simulate it and see the actual skies in your neighborhood where you are, which is a very nice tool. This is giving you a simulation. So this is not outside of where I live. I don't live in a farm, actually. Okay, but it gives you can upload your own picture, basically, of your area so that you can see what happened behind the buildings where you are, and building things like that. And I don't like this one in here. I like to remove it for right now. So where is this one? So this is the environment. So I'm going to remove it. No, actually, I simulated no daytime. So this is actually any time. This is the environment. Okay, so I removed completely what the sky looks like. Right now, you can't see the stars unless there is total eclipse, a solar eclipse. And this is how the sky would look like. This is the south. So if I'm facing south, this way, okay? Or yeah, this is the south, okay? So this is basically how I'm facing. Southwest is this way, and then north is this way, and east is this way for me. So depending on where you are, you can find your own location. You can spin the sky in here and see for objects. Let me look at the object of interest. First of all, you have in here, you can clearly see Jupiter and Saturn. If you turn on the names of your objects in here, so if you turn them off, you don't know. So at least keep them on, or you can search for an object that you're looking for, okay? You have a lot of stars in here, and you have Uranus in here. You have the sun, which is what am I looking at? Let me zoom out a little bit. Right now it's east, southeast. Okay, the sun is this way. Okay, so you have Venus immediately next to the sun, and you have Mercury next to it. Now Venus used to be called the morning star, and sometimes in the same culture actually it's called the evening star. And people realize that it was the same star. It's always following the sun. Either it sets after the sun sets, and it's called an evening star, or rises before the sun rises, and it's called a morning star. Okay? So that is basically, I'm sorry, did I say it backward? Yep, I did say it backward. Sets before the sun rises. So in this case, it's an evening star. No, it's a morning star. What am I talking about? If you see it in the morning before the sun, it's a morning star. If you see it in the evening after the sun, and it's the brightest object after the sun and the moon in the sky. As a matter of fact, if you click on it, its luminosity or its magnitude, absolute magnitude is negative 5.18. The smaller the number, the brighter the object. If you look at the sun, look at how much the number is going to be. Super negative number. Okay, negative 26.72. This is the brightest object in the sky. And if you guys know from negative numbers, the smaller they are, I mean, the bigger they are in magnitude, the smaller they are. In other words, negative 26 is definitely smaller than negative 3.886. So in this case, this is the object that is the second one in brightness. Mercury is slightly dimmer than Venus and so on and so forth. So let me click anywhere outside. I don't want to click on any object in here. And everywhere I click, I get an object in here. Okay, good. I don't want to click on any of them. So this line in here joining the sun to the other planets, where are they? They are below the horizon right now. So if I put back the horizon, you see that. So this line, Venus and where the sun is right now, let me go back and zoom in, and Uranus, Jupiter. Uranus cannot be seen tonight. It's because daytime is in here. Jupiter, Saturn, and then you have Mars in here. Okay, so you have almost all of the planets. Whereas Neptune, you can't see it because it's too dim, too far away. So what I'm going to do, I'm going to search for it. So let me search for Neptune, and it's here, one of the objects that I searched for it. And you can see where it is right now. So I have to zoom in on it to find it. I'm using the mouse to get into it. By this time, this is where Neptune, and it was not discovered until it was. This is by the way, its moon, Triton. So it was discovered later on, and this is a bunch of its moons actually that start to appear the minute we get closer to it. Look at the rings on it. Okay, it's an amazing software. Let me tell you this much, really, because it gives you a visual of where the object is in the sky. And it's actually moving right now, so I can stop it, at least so that the planet does not move. And nothing moves actually in it. Now I can study in here. It has one of these features that is similar to the red giants, the great red spot of Jupiter. Okay, so all of them do have stuff like some features on their surface like this one. But again, this is one of the objects in the solar system. This is one of its, I mean, it has a huge moon actually compared to the other, other planets in here. And then I have the other stars starting to appear. But this object, Neptune, was discovered by pure mathematics. Okay, people in the old days knew about the sun, of course. They knew about the moon. Those are two objects that were obvious in the sky, so they are outside of the Earth. Then they discovered, they knew about Mars also. They knew also about, I'm trying to keep them in order, okay? Mercury, that was known. They knew about Jupiter. They knew about Venus, and they knew about Saturn. They knew about seven objects that are odd compared to the rest of the objects in the sky. For example, if you look at any of the other objects in the sky, it doesn't matter which one, Aldebaran, for example, or Betelgeuse, for example, which are actually stars. if you look at those objects, they seem to be moving. They don't stick into one place in the, come on, man, I need to click out. Okay, is there any escape in here? No. I don't want to reload either. Okay, anyway, so look at, for example, one of the Origer, for example, Betelgeuse. Those are fixed and they don't change on a regular basis. Year round, you can see them in the forming the same geometries called constellations. Those constellations are shapes that different cultures associated them with different structures, and basically, like for example, the Orion, the hunter, which looks like a hunter hunting the Taurus, and he has his dog behind him. So we know the dog, which the dog where Sirius exists or Sirius exists, that's a different constellation versus that of Orion, versus that of, for example, the Taurus, and then you have all kinds of structures in there. Some stars, actually, one star does not change location at all, and that star is a very important star to know its location, and that is the polar star. Can I find it? Polaris. Okay, here it is. Okay. This one always, see, directly above the north, and this distance in angular distance is what is known as the, this is the latitude of where we are. This angle is about basically where we are in here in location. If you change another location, the angle will be slightly more or less depending on where you are, and this point does not change. This star does not change. The entire sky seems to spin, and I'm going to show you how it spins. So I'm going to turn on this one in here and make it spin faster. Look at the entire sky, night sky, basically spinning around Polaris. So Polaris is a good object to look at the to find yourself on, because it never changes the location. So as always, you look at it, that is where the north is pointing. All of the objects in the solar system, I mean, in the sky, the night sky, they change location. But as I was talking about, these objects in here, they don't change it really on a regular basis. They change it from year round, but they stay on the same constellation, the same shape. Other objects like this, Mercury, Venus, Jupiter, the ones I mentioned, they change from constellation to constellation. They move around, and they move around on a weekly basis. Some of them actually, like Mars, goes one way and then moves back and then moves the other direction. It's called the retrograde motion. So those objects, they were given a name. They were given planets versus stars. And star is a star, and a planet really means a moving star. Star that moves around, hops from location to location. So we knew about that distinction right away, that stars form in specific shapes called constellations, and this constellation appear on year round in the same location depending on where you are on the day. So you can make predictions based on that. However, the other ones, the wandering stars, that's what they were, they hop from constellation to constellation, and they move around all around, and they change locations, and some of them are moving one way and then they decide to move backward, and so they are kind of, that's why they were called wandering stars. So then, because of the influence of astronomy on our culture, we came up with 7 days. So we have this day of the sun, Sunday, the day of the moon, Monday, the day of Mars, which is actually Tuesday. In Latin languages, I think, at least in French, it's Mardi, and I think in Spanish, something similar to it. Wednesday is actually the day of Mercury. Again, in Spanish and Latin languages, including Spanish, they use this word in here that is like, in French, for example, it's Mercury. So I'm sure also the Spanish word. I'm sorry, I don't know much Spanish, so I know very little, to be honest with you. So probably some of you will help me with that. So how Wednesday is called, it's actually the day of Mercury. The day of Thursday is actually the day of Jupiter, because there is a god in the Greek language and the Germanic languages that is actually following that name, but it's actually in French again. It's also following the name of Jupiter, jeudi. And then Friday which is actually the day of Venus. And then, as you have guessed, the day of Saturday, which is the day of Saturn, okay? So those are 7 days. At that time, we didn't know about Uranus and Neptune. Had we discovered them then, we probably would have 9 days in the week. Wouldn't that be fun? Instead of working 5 days of the week, you work 7 days of the week and you have a couple of days off. No? Okay, at least somebody was honest. Good. Good. I don't agree too. I mean, I probably would have 4 days of 3 days off and so anyway, so this is basically the story of the solar system. So let me zoom in on this object because we're going to do that in here part of the lecture anyway. So let me find where Mercury is and zoom on it to see how it looks like. So obviously, it has actually features that are similar to the, oops, I don't mean to do that. Oh man, I lost it. It has features similar to the moon, and there are some new theories nowadays that speculate that actually this planet was a gas giant at some point, and now all is left of it is just its core, and it looks like it has collapsed on its own self, okay? Actually, there are some features in there suggesting that it has collapsed, and its density, as I was saying, is slightly less that of the Earth, indicating that its structure is mainly a combination of nickel and iron in its core, which is really the core that is left of whatever it's started with, and then some basically calcium-based materials, like, for example, earth and things like that. So this is, if you're looking at this dot, don't worry about it. That's actually a star. Okay? You can clearly see in here. Okay, so this so it's not a moon, in other words. So this is basically when we zoomed in on it. Venus, I already talked about the fact that it actually has a super thick atmosphere, and you cannot see much. I mean, even if you zoom on it, you cannot really see much off of it, other than the upper clouds in here that are extremely, like I said, heavy with carbon dioxide. Extremely, you cannot see its features inside. You have to use radar penetrating technology, like, for example, long wavelength enough so that they can penetrate the atmosphere and give you pictures. And that's exactly how we were able to take its pictures inside and so on and so forth. Okay. Okay, so this is in a nutshell how this looks like. Venus is extremely studied, and this we landed on it a lot, including recently Perseverance, that is still studying it, and there are a lot of landers on it, so it's not just this one. What is, should be on this side now. Okay, again, if I don't see it, I just look for it. Probably I'm not. Okay, here is Mars. Again, it has a couple of moons, but they're so small, and probably they are here. So this is Deimos, and the other one is Phobos, I'm sorry, and they're captured moons. But if I zoom on into the planet, it has a lot of features on its surface that we know of. It has ice caps on the North Pole and South Pole, and it feels, like I said, like the same almost rotation like the Earth in terms of day. And its atmosphere, its surface right now, it's a reddish star indicating, a reddish planet, I'm sorry, indicating that maybe it's at some point it had oxygen, and that oxygen, maybe the surface water basically broke up into its chemical components. Hydrogen left because of the low gravity of the planet that it has, so its escape velocity is very small. So the oxygen that remained for the most part recombined with the minerals that is mainly iron in there, and it gave it this reddish color in the air. Okay, and it's like a desert, really. It's a big desert, the entire planet. So one of the mysteries that we're trying to find right now about it is what happened to its water. Is it still underneath the surface? Could it have a life under its surface right now, and so on and so forth. This is one of the things that we're studying. It has some of the most fascinating geology in the solar system. It has the highest mountain on it, on its surface. It has also a lot of basically canyons. So it's really, it has a lot of features on it that are unique to itself. Again, that's a planet, a star, not a planet. Okay. So let me get into the next object after the Earth, and that should be Jupiter, because we are on the Earth. One of the things that is fascinating on this software, you can change your location, actually not just to another place on Earth. You can actually change your location to Mars and see how the night looks like from Mars if you are standing on its surface, or if you are standing on one of the moons of Jupiter, for example. So let me find what Jupiter is. Here it is. Okay. As you get closer to it, you see what almost what Mr. Galileo has seen. The first night he saw only 3 objects. He didn't see Io, actually. He saw Europa. Europa right now is behind Jupiter. You can clearly see in here. You have Ganymede, you have Callisto far away. This was one of the things that helped Mr. Galileo because when Copernicus looked at the data for analyzing the solar system and everything else, trying to fix the calendar from the time of Ptolemy, so he was tasked actually by the church to look into that calendar and fix it, because the theory from Ptolemy is that the Earth is the center of the solar system, and all of the objects, including the sun and the moon and the other planets and the other stars, they revolve around the sun, because that's what you see. I mean, if you go outside and look at for a couple of hours to the night sky, you will see everything is moving on the horizon and the above your head. I mean, so that's a natural assumption. That what I would have thought. I don't know about you, but that's the natural assumption that everybody thinks about it. So there was no reason why to suspect otherwise, because the sun comes in and they all rise from the east and they set in the west. Everything. Okay, with the exception that Mars, like I said, was clearly doing something weird. Sometimes it's going like everybody else, but at times it's going back and forth. So Ptolemy, now trying to fix that, he said, okay, the heavens are perfect. When God created Earth and the humans on it, they were sinless. The Earth also was perfect. But because of a human sin, it's not actually him who said that. It's actually the church that was proposing these ideas, that hey, then the Earth became imperfect, and that's why you see valleys and you see mountains and you see all kinds of things on its surface. But whereas the heavens are perfect, so everything must go in a circle, because there is nothing more perfect, symmetrical than a circle. So everything must be going in a circle. So that is basically the idea behind it. But how can you explain the fact that everybody is going on their circles except Mars is sometimes moving backwards? So what's going on with that motion? So what he suggested is, look, Mars is doing something unique to it in the sense that it's going in a circle around its own circle. So at times it's going in the same direction of the circle, so it's moving along with everybody else. But on the other times it's moving backward. I mean, it's still moving its own circle, but it's moving, appears to us moving backward because it's going in a circle around its own big circle. But that did not really fit the calculation perfectly, for at least when it's going to be there and everything else. So the suggestion was, we really need to make another correction, at least for Mars, and actually Venus we started to see that Venus also does that too. So the suggestion is that these planets are actually moving in circles, inside their circles, inside a big circle going around the Earth, and the idea became complicated. So Mr. Copernicus was asked by the church to fix things, because for example, if you rely on the calendar from the time of Ptolemy, trying to predict, for example, when is the next holiday, when is, for example, Easter next time around, or when is Christmas, instead of happening in the winter, you'll find that it's going to happen several months in the spring, and that's wrong. So the calendar was completely out of sync with what we know about the dates. Mr. Copernicus, when he looked at the skies, when he looked at the data, when he looked at it, he said there is something wrong. Actually, it's not the Earth that is the center of the solar system. It's the sun that is the center of the solar system. And everything, including Earth, is going around the sun. So we went from a geocentric hypothesis to a heliocentric hypothesis where the sun is actually the center of everything. And that was a problem. Problem among other things for the church, among other things, that we are not the center of everything. Apparently, we are just a note of the center of this, something else more important. So that was not accepted. So now when Mr. Galileo looked at this system, he immediately saw, and I know I stopped the motion, that these objects are actually spinning around something else. Let me expedite it, make it go faster. You can clearly see right now, if we wait a little later, that things are spinning around Jupiter. So the Earth cannot be the center of everything, because here are an example of several objects that don't spin around the Earth, but rather they spin around Jupiter. So that was a big, big blow to the ideas that were before there. And actually, so let me go back slightly in time, because that was actually an interesting event. That will give me how. Can I move back? No, I can. Okay, let me move forward. It's fine. Because you can clearly see Europa right now. You see Ganymede, you see Callisto. And at some point, Io was behind Jupiter. So that was the first night, actually, when Mr. Galileo went and looked at these stars. The next day, he saw the fourth one, namely Io. Io was very close from Jupiter, and every 42 hours, it goes once around the planet. So it's really a very, very fascinating object by itself, and it's So it's not centered around those. So I was moving backward. That's fine. Anyway, the point being in here is this system helped a lot the work of Mr. Copernicus, and that was in support of him. Furthermore, he looked at actually the moon, and he saw that it has also mountains and valleys. So that idea that Earth is the only one that is messed up because of a human sin is also. So Mr. Galileo did a lot of things for us. These four moons, namely Europa, Io, Ganymede, and Callisto, are known as the Galilean System because of the way that he discovered them. So again, Callisto is very far away, okay? And so sometimes they seem to be moving back and forth, and it's because of our location in here and the way that, the fact that this one is actually moving around the Earth. Let me stop it right here. So this is the first night what he saw. Okay, fascinating. Europa has a super thick ice on top of it. And then underneath, we know it has an ocean, not only in the ocean, but it has actually a salty ocean. Actually, it has more water in it than all of the waters on Earth. So that's one of the things that is that we know. I mean, we know actually from the materials that are escaping its surface, and that's how we know it also. So Europa could harbor life as we know it in its actually like oceanic life, basically the one that we know it on Earth, and it's getting its energy from the inside of its core because of the tidal work. Because at times it's going, like right now, all of the other three objects, the main three objects, including all the other objects, including Io, Jupiter, Ganymede, and Callisto, are pulling it on one way. If you wait a little longer, we'll find them actually pulling on it on the other way. So as if you have dough and you're trying to work it out. So its material is being sometimes pulled one way, sometimes pulled the other way, and sometimes actually pulled evenly. So its surface is worked out all the time, and it has this energy from the inside. This is not as drastic, actually, as dramatic as it's happening actually on Io. Io has even worse than that because it's closer to Jupiter, and it has, because of the tidal forces basically being pulled over on one way or the other, especially with the other big moons in here, including Europa also, it's pulling on it too. So it's being worked out even stronger, and it's because it's near Jupiter. So it has a lot of this activities on it, and it has volcanic activities on its surface, and it's the most active volcanic object in the solar system. So it's really a fascinating object. Same thing with Ganymede and Callisto. They also have, we think that they have also water underneath their surfaces too, because although if you look at Callisto, for example, let me zoom in it. Okay, you will see that its surface has more impacts on it. That means that it was subject to a lot of impacts, which means it has less activity than if you take, for example, one of the other less geological activity, let's say, for example, compared to Europa, if I can find it again, whose surface seems to be impacted, I mean, less craters on its surface, and it seems that it's being weathered. There seems to be phenomenon going on its surface here. So this is Jupiter. There are, as I said, more than 70 moons that we know. Okay, so these are just some of the big ones. Then comes Saturn. And Saturn also has at least one huge moon and a lot of other moons too. One of its moons that you probably saw it in the movie Interstellar is Titan. This is the only object outside of the inner planets. The inner planets are from Mars and inward that we landed on. We landed actually on Titan too, which is one of its moons. The Titan surface looks very, very similar to that of the Earth. It has oceans, but instead of water, it has oceans of methane. Okay. And it has actually a thick atmosphere, and its pressure is similar, slightly higher than that of the atmospheric pressure on Earth. So surface temperature extremely cold, and it has a rocky structure, and the rocks are actually ice, water ice. Okay, so this moon seems to be fascinating, and that's one of the things that if we can't. We probably could serve, because its atmosphere is actually nitrogen. It's mainly nitrogen, actually, and it's you could actually theoretically, at least, you could take its. This is another moon actually from Saturn. You could extract the oxygen from the water, that is from the form of ice, and breathe it, and potentially, because the surface pressure is not that high, surface temperature is high, so you need to have surface temperature is very cold, so you need to have protective gears against the cold temperatures. But other than that, you could have a breathable air easily. That's why in the movie Interstellar, they show you, I don't know if you guys have seen it or not, after the end of the movie, they all seem to have ended up, at least the main two characters ended up on a base on this moon. And it's always used as because it's really, for us as humans, probably it's the best place after the Earth. I mean, the others are no good. Okay, including Mars, by the way. Okay. So again, this is the planet itself. It has this huge ring system around it. And the ring of systems, they're actually classified in different groups, actually. And they're being shepherded by tiny moons around them, and that's why you see them in there. Actually, the entire moon, it's the entire rings themselves. Basically, like I said, they are very, very thin, and they're made up mainly of ice particles and small rocky particles around the planet. And like I said before, all of the outer planets have this same features in here. We're still studying this object in here. We sent a probe to Jupiter, and Cassini actually was the last one to be basically dumped on the surface of Saturn. Okay, so that is did not go into the surface. Actually, even for Mars, for Jupiter, we did not actually land on it. We don't know what's the surface look like, if it has they have surfaces at all. These are mainly hydrogen and helium planets that they're called gas giants, versus the frozen planets, which are mainly also gas giants, but they are not like this too. And they are Uranus and Neptune. the last two of the solar system, and Uranus is in here somewhere. So I probably have to zoom in there to find it, okay? And again, it was not discovered by it was not discovered until later on when we saw that there is something weird about the motion of Neptune. So that's one, the hypothesis for it also was basically postulated, and it was found later. Or was it? No, it was found by accident, I'm sorry. Yeah, Uranus. Now you cannot see it with small telescopes from Earth. Both Uranus and Neptune have this bluish color, and they have ring systems also, and they have strong winds on their surfaces. As a matter of fact, their winds are a lot stronger than a lot of the other planets. So this is the ring system, and this is how the planet looks like. It has Miranda, which is one of its fascinating moons, and Titania, which is also a big moon. So it has a lot of moons too. So this is, in a nutshell, Aldebaran. You have a lot of the solar system objects in here. So we spent most of the time on this software, but it's actually a very nice software. It brings you more of the things visually to them. Obviously, let me turn on the daytime again. What is the daytime? Here is the daytime. This is how they look like right now. So, oops, I turned it off again. And this is how the horizon looked like. So what I was looking at in here is below the horizon, way below the horizon. So right now, this is how the sky looked like. So if I really want to simulate what happened, for example, tonight, I can change the time to, this is 5 p.m. actually. So 7 p.m. No, 19 is 7 p.m. So let's make it into 10 p.m., which is 2200. So this is how the night would look right now if I look at the west from where I am at. Okay. And let me turn on the constellations. Constellations, here they are. And let me turn on their shapes so that you can see how they look like. So again, these are the constellations, and this is what people have basically described in the past based on what we know in here. So it's a good idea. This is where Polaris is. Okay. So this is how you find it. There is a pan in here, so it looks like this one. So extend this, the top of the pan by 1 of its length, 2 of its length, 1/3 of its length, and the last one is going to be your star. So this is where the north is, and this is where we are right now. Okay, the north is this way. So if I look at it tonight, it's going to be somewhere in there. So again, this is something fascinating, as I was saying. Let me close this software and let me stop sharing first of all. And let's look into the notes that we have. Okay, so let me share briefly, okay? I know we spent a lot of time on this one. So you guys have seen the solar system. I already talked briefly about how it was formed. The sun is its core, and this is the power of most of its energy coming from nuclear reactions, and there is actually one main nuclear reaction that converts protons, namely hydrogen, into neutrons, and at the end process, actually, form hydrogen atoms combine to form the helium atom, plus a lot of energy. How do we know that? Did anybody go to the core and observe the nuclear reaction? No. The byproducts of the reaction are exactly what is needed in terms of energy, because people theorized in the past that we didn't know about nuclear reactions up until the 1930s, when we actually had better understanding of nuclear energy. But at that point, we didn't know about it. So there are only two candidate potentials for how the sun gets all of its energy. Either through some sort of a chemical process, burning of some fuel, for wood, for example. Maybe the sun is made up of a lot of wood, all of its mass is wood. Based on Newtonian mechanics, we can estimate its mass. We know its mass to be about 10 to the power 30 kilograms, or 10 to the power 31 kilograms, actually. So that's a lot of wood. Could it burn Or maybe it's fuel. At that time, we also learn about the fuel, coal, for example, or other fuel, for example, the carbon-based fuel. Could it be made out of those materials? And if I burn it, how much would it take for me to get all of that fuel burned? It turns out, because of what we know about chemistry and how much energy is delivered, and because I can go outside now and have a pool of water, I know how much water there is in that pool. Let's say, for example, I take a cubic meter of water and let it outside for about an hour. Measure its temperature now and measure its temperature an hour later. I can find how much temperature it has increased. Based on that, I can see how much heat was collected on the water, because we know the specific heat times the change in temperature times the mass of the water gives me the amount of heat that was added in joules. Actually, we can find it. Now we know how much energy was added. If I know how much the surface of that water is, then I can tell you how much power is being delivered from the sun on that surface. If I multiply that by the surface of the earth, I can tell you how much power is being delivered to the earth from the sun. But if I know how far the sun is from the earth, then I can tell you how much power just is going to be proportional to the entire surface where the earth is sitting. So this is how much tiny energy I'm getting, but that energy must be spread throughout the entire sphere where the earth is sitting, of radius 150 million kilometers, basically. So that energy must have come from, at some point, from the sun. If I do this calculation, it turns out the power of the sun is about 4 times 10 to the power 26 watts. 4 times 10 to the power 26 joules every second is coming from it. How much wood or how much coal would I need? I know the mass of the sun. How long will it take for me to go through that entire energy to consume it? We can do the calculation and find that the sun is about 10,000 years old. After 10,000 years old, it's going to run out of energy. We knew in the early 1900s that that's not true, because geological studies at that time suggested that the earth was several million years old. And those studies also suggest that the sun has been shining at least for that long. So the hypothesis that the sun is made up of some sort of a fuel causing its energy to be dissipated is not correct. So there is another possibility. Here is another possibility. Remember, the sun and all of the planets were a big gas of tiny particles, and they start to coalesce together and form those big objects. Could it be that the gravitational energy is being converted to kinetic energy, because as these objects get closer and closer, they lose potential energy and convert it to kinetic energy, and that kinetic energy is what we're looking at, heat, basically. If we assume that the sun shrinks about 5 centimeters a year only, so this is how much it is today, 5 centimeters later next year, it's going to shrink in size. That should be enough energy to sustain the sun for about 100 million years. So that seems to be good explanation at that time. But immediately after that, we started to discover radioactivity and radiometric dating, and we knew then that the sun has been shining for at least 4.5 billion years ago. So 100 million years doesn't cut it. So this process has to be crossed. It's no good. So there must be another process, and it was really a puzzling issue. How can we explain the energy that we're receiving on the Earth from the sun and all of this, the entire solar system? And it's been doing this for 4.5 billion years. So there is no chemical process that can account for that energy. There is no physical process involving converting potential to kinetic energy. Because if that's possible, then that 5 centimeter hypothesis need to be made it's even different, and then it's not enough energy to do it. So it's really not going to work. So until 1930s, when Mr. Hans Bethe suggested that, because of what we know about nuclear energy, that look, if I do the math, he says, take 4 protons, 4 hydrogen atoms, basically. And because of the extreme high temperature in the sun, and because of the extreme high pressure in the core of the sun, these 4 protons are moving super fast because of the heat, and they're getting very close from one another because of the pressure. So at some point, 2 of them will actually fuse, because proton and proton are both of them positive. So they repel one another. But if they get very close because of this high pressure and high temperature, then they will fuse. And in doing so, one of them will change to a neutron. Okay, now what? You don't have energy, because if you do the calculation, that's not enough energy. What you ended up with in this case is a different isotope of a hydrogen. Instead of hydrogen, normal hydrogen, now you have a hydrogen that is made up of a proton and neutron. He says, okay, the next step, so when he calculated the probability for this happening with this temperature and this pressure, he found it extremely small, almost negligible. But if it's just enough because of a huge amount of matter, then this heavy isotope of hydrogen will attract another proton to it with the same process. And now, instead of having one proton and one neutron, which is an isotope of hydrogen, you have two protons and a neutron, which is an isotope of actually helium, a lighter isotope of helium. Now you're ready, because if you have two of this is a process, there is a lot of them in the sun. So there is a potential of two of them, of this lighter isotope of helium, then they will fuse, expel the extra protons, and they will form the regular isotope of hydrogen. I mean, the regular isotope of helium, I'm sorry. And that will deliver a lot of energy. If you do the calculation, you find a tremendous amount of energy coming from it for every single process. And multiply that. I mean, it's not a lot of energy. It's only 27 mega electron volts, which is extremely small in joules. But you have a lot of them happening in the sun that could give you that 4 times 10 to the power 27 joules per second. And it could last for billions of years, given the amount of the mass of the sun. So because of the mass of the sun, it could last, according to his calculation, about 10 billion years. So from the time the sun was basically born until now, we are midway in its, so the sun is in prime life, basically, according to this process. It's all good and dandy, except that we need to verify this hypothesis, okay? Yes, you explain the energy, but if you only think you can explain something, that is not good enough. You need to tell me something else. A byproduct of that operation was neutrinos, according to his calculations. If we can discover those neutrinos, then we're in business. Sure enough, later on, the Kamiokande lab in Japan and the Sudbury lab in Canada, they were able to find those neutrinos. So indeed, that's exactly how we know it. Isn't this interesting? How we know how the sun produces its energy? I talked about the inner planets and the outer planets in detail. The big difference of them is the inner planets are rocky planets and small, and the outer planets are mainly gas, okay? And they are bigger in size. The outer planets have moons, a lot of them. The inner planets do not really have moons. We'll talk about it separately. We'll probably have to meet about that. Okay, I'm answering one of your questions on private question, okay? So again, the outer planets have moons. The Earth is an exception to the rule. It has a big moon, okay? Which really is a big topic by itself. So the Earth's moon most likely happened due to a collision of the Earth with another, it's actually Mars-sized object, it's a big object. And that's how we know today how the moon is formed, okay? And then failed planet formations are the dwarf planets. Okay, I think we talked about everything there is in the solar. This is how the solar system formed, and this can be explained by the conservation of angular momentum. And this is, again, different look at Mercury with its properties, okay? 430 degrees Celsius during daytime, and nighttime it gets extremely cold. Venus has this almost the same size of the Earth, but its conditions are really not good at all, okay? And we talk about the Earth. This is actually Mars, okay? Jupiter, and it's big size, and it's basically 82% hydrogen, 17%, just similar, almost similar to the sun in terms of structure, okay? I think it has an inner core, but what gives it its magnetic field, which is extremely strong, is it's actually liquid hydrogen, which is kind of a weird structure that you can think of, but it's because of the extreme pressure that is coming from the planet. Here are its 4 moons, the ones that I was talking about it. This is Io. Io actually is the second one in size. Europa, but it's a closer one of the 3 out of the 4 to Jupiter, and looks like it's extremely heavily basically active in terms of geology, surface changing all the time. Second one is actually Europa. Europa also has some geological features indicating activity. If you go further away from it, this is Ganymede and Callisto, and they are actually but this shows more activity in it than this one, because this one is still heavily impacted by it has a lot of crater impacts, indicating that it does not go as much as the others in terms of its geological surface. Okay, so this is actually the look at Europa. This is what I was talking about in here in terms of its ocean. Okay, this is a big, thick, it's a mile high or more of ice. Okay, now Saturn, talk about its features. This is the only object we landed on, and this is the pictures from actually its moon Titan. Okay, Uranus, as I was saying, it's spinning backward, unlike the other objects. Neptune has rings also in it. And Pluto's story is another one in terms of how we used to classify it as a planet, and then we declassified it because of the fact that we found a lot of objects similar to it in the Kuiper Belt, and also the fact that it has other properties that are not similar to the other planets. And we talked about the Earth Moon and the way that we studied it a lot, and we have collected rocks from it. Based on that, we knew that it shares a lot of structure with the Earth. So part of it is actually coming from the Earth. That's why the hypothesis that it was created in a collision is strong. Okay. And so this is probably what happened to it. This object called Theia is the one that collided with the Earth. And then it formed this big ring in here at some point, and then the matter started to coalesce again, forming the current moon. Moon has unique features in here because of how it collects light from the sun. It's going to be a new moon, go through the cycle in here, quarter moon, waxing because it's increasing actually in here. And then it becomes a full moon, and then it becomes waning in all of its stages. And it's fascinating that you can observe, actually right now we are somewhere in here. The new moon happened last week on Thursday or Friday. No, Wednesday. Wednesday of last week was the new moon. So we are just around this point in here. So if you go and start observing, actually this is the best time to observe the skies, because the moon does not ruin it for you. It does not send a lot of glare in front of your telescope. If you are here, then there's a lot of light coming from the moon, so it ruins your, especially the objects near it. Again, the moon is tightly locked with the Earth. That's why we see only one face to it, because it spins as fast as it goes around the Earth. So that's why it faces only one, gives you one direction all the year round. And the tidal forces are actually causing a lot of effects on the moon, and actually on the Earth too. And this is the eclipses. This is the solar eclipse, and the lunar eclipse is the opposite to it. Okay. So this is in a nutshell your chapter. I will, okay, like I said, oops, did I stop sharing the screen in here? I did. So we still have 2 more chapters from this class, and I will, we will meet again at least this coming to Thursday for the next chapter, and the next week, and then we'll have exams, and we'll have to prepare for them, and including the last exam for this section and the last final, which is going to be comprehensive. Okay. One of you asked earlier, and I think it's related to the question that is asked in private too. I dropped the lowest grade for the exam, so if you could not make an exam or you did not make an exam, you will see that grade is being graded. It's dropped. I usually do not make up exams because of the fact that I dropped the lowest grade, okay? So that is in a nutshell what we have. So unless you guys have questions or you would want to meet in private, I'll be more than happy to discuss these things. I'll stop the recording and I will see you guys on Thursday.
Professor?
Yes.
I have a question. Are we still posting anything in the discussions at all? Okay.
Unless you, yes, okay?
Okay, thank you.
Thank you guys.